The internal combustion engine is not dead. However, its role as the default power source for mass-market passenger cars is changing, driven by thermodynamic realities that engineering alone cannot bypass. At its core, an internal combustion engine performs a specific task. It converts the chemical energy stored in fuel into mechanical work through controlled explosions inside a cylinder. In standard spark-ignition gasoline engines, this conversion follows the four-stroke Otto cycle. The mechanism pulls a fuel-air mixture in, compresses it, ignites it with a spark to force the piston down, and pushes the exhaust gases out. Compression ignition engines use the diesel cycle. They operate on the same mechanical principles, but omit the spark plug, instead relying on a much higher compression ratio to heat the air enough to spontaneously ignite the injected fuel. Regardless of the exact cycle or how precisely the valves and injectors are tuned, all heat engines hit a strict thermodynamic ceiling known as the Carnot limit. Physics dictates a maximum possible efficiency based on the temperature difference between the combustion source and the outside environment. This data visualization breaks down where 100% of that fuel energy actually goes. At their absolute best operating point, well-optimized production gasoline engines convert only 35 to 40% of the fuel's energy into useful mechanical work. Diesels, benefiting from that higher compression, reach about 40 to 45%. The remaining majority of the energy is unavoidably lost as heat. It radiates out through the exhaust and the cooling system, an inescapable consequence of the second law of thermodynamics, pressure ratios, and friction. Over a century of rigorous mechanical optimization has pushed production engines right up against this physical ceiling. Incremental improvements to combustion timing or materials can no longer yield massive efficiency gains. By abandoning combustion entirely, the battery electric vehicle takes a different thermodynamic path. Instead of relying on heat, an EV uses a permanent magnet synchronous motor to convert electrical energy directly into mechanical energy. Across a wide range of speeds, this electromechanical process operates at 90 to 97% efficiency. Supplying that motor requires a chemical storage system, but modern lithium-ion cells also execute their charging and discharging cycles with efficiencies in the high 90s. To accurately compare these two systems, we have to expand our evaluation boundary past the vehicle itself. We use a metric called well-to-wheel efficiency, measuring the total energy retained from the original source all the way to forward momentum. This parallel flow visualization maps those system boundaries side by side. For a typical gasoline vehicle, the full refinery-to-wheels chain factors in the energy spent extracting, refining, and transporting the oil, plus the massive thermal losses at the engine. The final mechanical output is a severe drop, retaining just 20 to 25% of the original energy. The grid-to-wheels efficiency of a battery electric vehicle factors in the grid generation, transmission over power lines, charger losses, and the motor. It typically retains 70 to 80% of the original grid energy. Battery electric drivetrains are capturing the light passenger market because they operate within a superior systemic boundary. The physics of heat engines set a firm ceiling that combustion simply cannot overcome. That efficiency advantage, however, carries a strict life cycle caveat. Operating an EV is clean, but building one is not. Manufacturing a battery electric vehicle, particularly the mining and assembly of its lithium-ion pack, is significantly more carbon-intensive upfront than casting a conventional combustion car. This creates a carbon break-even point, the specific mileage at which the EV's clean operation finally offsets its dirty manufacturing, relative to a gas car. This line graph plots life cycle emissions over miles driven. Studies in typical markets place this critical break-even threshold between 15,000 to 25,000 miles. Over a long lifespan, an EV emits roughly half the lifetime carbon of an equivalent gasoline car. That ratio is a moving target. As regional power grids phase out fossil fuels and add more renewable energy sources, the operational emissions of an existing EV drop, improving its lifetime carbon footprint. Conversely, where electricity is generated mostly from coal, the break-even mileage extends significantly. But this data justifies decarbonizing the power grid in parallel rather than abandoning electrification. An electric vehicle acts as a hardware extension of the local power grid. Evaluating its impact requires a systems engineering perspective focused on regional infrastructure rather than simple tailpipe output. That geographic complexity is directly reflected in global market adoption. In 2025, global EV sales surpassed 20 million units, representing about 1 in 4 new vehicles worldwide. China drove the vast majority of that volume, accounting for 62% of global EV sales, with its domestic market pushing well past a 50% electric share. The United States market reacted very differently. EV sales slipped 4% in 2025, and then fell a sharp 28% year-over-year in the first quarter of 2026, driven largely by the expiration of a major federal purchase credit. Consumer sentiment followed suit. Surveys in early 2026 revealed that only 11% of current combustion vehicle drivers intended to purchase an EV next, a steep drop from 31% just 2 years prior. In Europe, the transition has been strictly enforced by policy. The European Union's original 2035 rule effectively banned the sale of new combustion-only cars, but pushback from major automakers and shifting political blocs forced a revision in December 2025. The EU softened the total ban into a 90% tailpipe carbon reduction target. This revision explicitly allows the continued sale of plug-in hybrids, mild hybrids, and vehicles running on certified synthetic alternative fuels beyond the 2035 deadline. Between sudden drops in consumer intent and shifting legislative mandates, the early, aggressive, all-electric timelines have fractured. Automakers are being forced to heavily adapt their engineering strategies. This adaptation has made the hybrid electric vehicle the most consequential near-term automotive trend in the United States. Conventional hybrids, plug-in hybrids, and range-extended EVs saw a massive sales surge, hitting 756,000 units in the fourth quarter of 2025 alone, a 57% increase year-over-year. The appeal is rooted in mechanical pragmatism. Hybrids capture regenerative energy during braking and deploy it to assist the engine. They drastically cut fuel use without ever requiring the user to locate a public charger. They eliminate range anxiety completely and remain fully operational regardless of extreme climate conditions that might degrade battery performance. Realizing the necessity of this middle ground, several major automakers have pivoted away from their binary plans to switch abruptly from combustion to fully electric lines. Instead, engineering resources are flooding into flexible platforms. These shared vehicle architectures accommodate a combustion drivetrain, a hybrid layout, or a massive battery pack, all on the same assembly line. Hybrids are an optimal intermediate engineering solution. They successfully decouple immediate fleet-wide emission reductions from the inherently slow rollout of a national electrical charging grid. While the passenger car transitions, a much harder set of engineering cases exists just beyond light-duty transport. This scale visualization compares the core constraint holding back heavy industry, gravimetric energy density. Measured in watt-hours per kilogram, it reveals the immense difference in stored energy between 1 kilogram of chemical fuel and 1 kilogram of lithium-ion cells. Sectors like long-haul trucking, aviation, and marine shipping require massive amounts of stored energy to cover vast distances. Moving that energy into a battery system pushes directly against the physical limits of weight. In commercial transport, every extra kilogram of battery pack directly cannibalizes the allowable payload capacity. Adding enough batteries to move a semi-truck 600 miles leaves very little legal weight limit left for actual freight. Logistics networks also rely on rapid turnaround. The speed of pumping high-density liquid fuel vastly outperforms the megawatt charging times required to replenish commercial-scale battery packs. Battery pack costs continue to fall steadily towards $75 to $100 per kilowatt-hour, crossing parity for light cars. But cheaper batteries do not solve the physical penalty of mass. In heavy transport, the extreme energy density provided by chemical fuels is a non-negotiable physical requirement. This guarantees the combustion cycle will remain highly relevant for decades. Because the mechanics of combustion are necessary for heavy industry, engineers are turning to synthetic fuels, or e-fuels, to decarbonize the process without changing the drivetrain. Producing e-fuel is an exercise in reverse chemistry. Facilities capture existing carbon dioxide directly from the atmosphere or industrial exhaust and combine it with green hydrogen derived from water. The thermodynamic conversion losses during this production are massive. However, if the entire synthesis is powered by renewable electricity, the final liquid fuel approaches net zero life cycle emissions. It burns in a standard engine but adds no new carbon to the atmosphere. Major investments are scaling this technology from the lab to commercial reality, most notably Porsche's operational e-fuel production plant in southern Chile. Concurrently, manufacturers are developing direct hydrogen combustion engines. These heavily modified blocks burn pure hydrogen gas for off-road and heavy-duty applications, bypassing carbon entirely while maintaining the durability of mechanical pistons. For the world's most demanding physical workloads, the future of decarbonization lies in altering the chemistry of what we burn, rather than completely abandoning the mechanics of how we burn it. A clear dividing line has emerged. For mass-market passenger cars, falling battery costs and an unclosable thermodynamic efficiency gap mean the future is electric. But the strict rules of gravimetric energy density ensure that the internal combustion engine is not obsolete. It will survive and evolve in commercial shipping, aviation, and heavy logistics for decades to come. The internal combustion engine's era as the default answer for every single mobility problem has ended. In its place, we are entering a highly specialized, bifurcated engineering future where the workload dictates the drivetrain. If you are an engineering professional looking for deeper structural analysis, complete thermodynamic modeling, and detailed life cycle data on modern drivetrains, visit ProReadyEngineer.com to explore our technical resources.